This is a recast of the 6,600-word piece, Backpropagation Neural Networks, BNNs, from Schneepat.com. This article discusses the concept of backpropagation neural networks, BNNs, their structure, training process, optimization techniques, and applications in various industries. It also highlights the advantages, limitations, and challenges associated with BNNs, as well as strategies to improve their performance. Let's listen in.
Today, we're talking about backpropagation neural networks, also known as BNNs. These are a type of artificial neural network that have gained popularity due to their ability to efficiently solve complex problems with large amounts of data.
That's right. BNNs are composed of multiple layers of interconnected artificial neurons that mimic the structure and functions of the human brain. The key feature of BNNs is the backpropagation algorithm, which allows them to learn and adjust their weights and biases in order to minimize the error between the predicted output and the desired output.
The backpropagation algorithm is really important because it allows the network to continuously refine its predictions by minimizing the difference between actual and predicted outputs. And this algorithm makes use of a training set to iteratively update the network's parameters until reaching an acceptable level of accuracy.
Absolutely, and BNNs have been successfully applied to various fields, including pattern recognition, image processing, speech recognition, and natural language processing. They offer a powerful mechanism for solving complex problems such as predicting stock prices, diagnosing diseases, analyzing medical images, customer segmentation, and object recognition in robotics.
That's right. BNNs have a wide range of applications in industries like finance, healthcare, marketing, and robotics. In finance, they can be used for predicting stock prices, portfolio management, and fraud detection. In healthcare, BNNs help in diagnosing diseases, analyzing medical images, and drug discovery. And in marketing, these networks assist in customer segmentation and personalized recommendations. They are even relevant in robotics for tasks such as object recognition, localization, and navigation.
Indeed. Now let's talk about an important aspect when it comes to BNNs: overfitting. Overfitting occurs when a model becomes too complex and starts to memorize the training data rather than capturing the underlying patterns or generalizing to new unseen data.
Overfitting can significantly hamper the performance and predictive accuracy of Bayesian neural networks, BNNs. To combat this issue, several strategies can be employed, such as regularization techniques like L1 and L2 regularization, early stopping, and dropout. These techniques aim to control the complexity of the model and prevent overfitting by penalizing overly large weight values or reducing the impact of certain neurons.
Exactly. By using these techniques, we can promote the creation of a more generalized and robust model that is capable of making accurate predictions on unseen data. It's crucial to address overfitting to ensure the reliability and effectiveness of BNNs.
Now let's move on to understanding the structure of BNNs. They typically consist of multiple layers, including an input layer, one or more hidden layers, and an output layer.
That's right. The input layer is responsible for receiving external data or patterns and passing them to the hidden layers. It represents the initial stage of the neural network, where the input features are transformed into a format that can be processed by the network.
And the hidden layers perform complex computations and transformations on the input data. These layers play a crucial role in extracting relevant features and patterns from the input data. They introduce nonlinearity into the network through the use of nonlinear activation functions, enabling the network to model complex relationships between inputs and outputs.
Finally, the output layer synthesizes the results obtained from the hidden layers and produces the final output. Each layer in a BNN has a specific purpose, and collectively, they enable the network to learn and make predictions.
Understanding the structure of BNNs is essential in effectively designing and training these networks to achieve the desired outcomes. It allows us to optimize their performance and ensure that they are able to make accurate predictions.
Absolutely. BNNs have become an essential tool in the field of artificial intelligence and machine learning due to their versatility and effectiveness. They offer a powerful mechanism for solving complex problems and have wide-ranging applications in various domains.
That's right. And one important aspect of BNNs is understanding the role of neurons and activation functions. Neurons are the building blocks of these networks responsible for processing and transmitting information. Each neuron receives inputs from multiple other neurons and applies an activation function to transform these inputs into an output.
Activation functions play a crucial role in determining the behavior of the neuron and the network as a whole. There are several common activation functions used in BNNs, such as the step function, sigmoid function, and rectified linear unit, ReLU function. Each of these functions has unique properties that can impact the learning ability and convergence of the network.
Yes, and the choice of activation function depends on the specific problem and desired behavior of the BNN. It's important to consider how different activation functions will affect the network's performance and whether they are suitable for the task at hand.
In addition to understanding neurons and activation functions, weight and bias initialization is another critical aspect of building BNNs. The initial values assigned to these parameters greatly influence the training process and the performance of the network.
Absolutely. A careful initialization strategy is required to avoid problems like vanishing or exploding gradients and to achieve faster convergence during training. Various methods have been proposed for weight initialization, such as random initialization, Savior initialization, and He initialization. Similarly, bias initialization can be done using constant values or setting them to 0.
Another ethical consideration is the impact of BNNs on employment. While these networks can automate tasks, they may result in job displacement for human workers. Finding a balance between the benefits and potential harms of BNNs is essential to ensure their ethical development and implementation.
Well said, Samantha. It's important to consider the ethical implications and societal impact as we continue to develop and utilize BNNs. Balancing the benefits and potential risks is crucial to ensure that BNNs are developed and implemented in an ethical manner.
Absolutely, Avery. As technology continues to advance, it's essential to address these ethical considerations to ensure that BNNs are used responsibly and for the betterment of society. The choice of suitable initialization techniques for weights and biases is crucial to ensure a stable and efficient learning process in BNNs. It's important to find the right balance that allows the network to learn effectively without getting stuck in suboptimal solutions.
Moving on from initialization, let's talk about the backpropagation algorithm. It's a crucial component of BNNs that enables efficient training of the network by adjusting the weights based on calculated error gradients.
The backpropagation algorithm works by propagating the error backwards through the layers of the network. This allows the algorithm to determine how much each weight contributes to the overall error and update them accordingly. It's a gradient descent approach that iteratively adjusts the weights to minimize the error.
The backpropagation algorithm has proven to be highly effective for training neural networks. It allows them to learn complex patterns and make accurate predictions. Its widespread adoption signifies its importance in the field of artificial intelligence and machine learning.
That's right, and it's important to note that the backpropagation algorithm is not without its limitations. It can be computationally expensive and prone to getting trapped in local optima. However, ongoing research and advancements continue to enhance the algorithm, making it a fundamental tool in the field of artificial intelligence.
Now let's discuss the forward pass, which is an essential step in training a BNN. In this step, the network takes an input vector and computes the output values for each neuron in each layer.
The forward pass involves multiplying the inputs with their corresponding weights and applying an activation function to the result. This introduces nonlinearity to the network, allowing it to model complex relationships between inputs and outputs.
The output values are then passed on to the next layer, where the process is repeated until the final layer is reached. This process of passing information forward through the network enables the BNN to generate predictions and learn from the error between these predictions and the actual outputs.
Overall, the forward pass is a crucial component of backpropagation as it sets the stage for the subsequent steps in training the BNN. It allows the network to generate predictions and learn from its mistakes, improving its performance over time.
And as we wrap up today's discussion, it's important to remember that BNNs have emerged as a powerful tool for addressing complex problems in the field of artificial intelligence and machine learning. Despite their challenges, ongoing research and advancements are continuously addressing these limitations and enhancing the performance of BNNs.
And with these advancements, we can expect BNNs to play an even more significant role in the future, contributing to advancements in various industries and shaping the way we approach complex problems.
Absolutely. Now let's dive into the details of backpropagation and how it plays a crucial role in adjusting the weights and biases of the neural network. In the process of backpropagation, the output error is calculated by comparing the predicted output with the actual output. This error is then propagated back through the network, layer by layer, using the chain rule of calculus.
That's right. During the backward pass, the derivatives of the activation functions and the loss function are evaluated. These derivatives provide information about the sensitivity of the outputs to changes in the weights and biases. Using this information, the weights and biases are updated using a gradient descent optimization algorithm.
The optimization techniques in backpropagation further enhance the process. One such technique is momentum, which aims to accelerate convergence by incorporating information from past weight updates. By introducing a momentum coefficient, we can determine the contribution of past weight updates to the current update.
Another technique is learning rate decay. This technique modifies the learning rate over time to fine-tune the weight updates. Gradually reducing the learning rate allows for more precise adjustments, leading to better convergence.
And let's not forget about weight decay. This technique prevents overfitting in neural networks by adding a penalty term to the loss function that discourages large weight values. It helps ensure that the network doesn't become too specialized to the training data and can generalize well to unseen data.
These optimization techniques are essential in enhancing the efficiency and performance of backpropagation in training neural networks. They allow for faster convergence and better generalization capabilities.
Absolutely. Now let's shift our focus to training and learning in BNNs. During the training process, BNNs aim to minimize errors by adjusting the network's weights and biases. This is done through the backpropagation algorithm, which propagates the errors backward through the network.
The first step in training is forward propagation. Inputs are passed through the network, and the corresponding outputs are computed. Then the errors are calculated by comparing these outputs with the expected values.
Using these errors, the backpropagation algorithm computes gradients of the error function with respect to the weights and biases. These gradients provide information on how the weights and biases should be adjusted to reduce the overall error.
And that's where gradient descent comes into play. The algorithm adjusts the weights and biases in the direction that minimizes the error, moving towards an optimal solution. This iterative process continues until the network converges to a point where further adjustments do not significantly improve performance.
And let's not forget about the importance of training datasets. These datasets are crucial for BNNs to learn and improve their performance. They provide the necessary input for the network to adjust its weights and biases, optimizing its ability to accurately classify and analyze various types of data.
It's important to note that the quality and diversity of training datasets significantly impact the generalization ability of BNNs. A diverse and representative dataset allows BNNs to adapt and perform well on unseen data.
That's right. Selecting appropriate training datasets becomes pivotal in ensuring the success and effectiveness of BNNs.
And with that, we've covered the main points from the article. Backpropagation plays a crucial role in adjusting weights and biases, and optimization techniques enhance its efficiency. Training and learning in BNNs involve minimizing errors through the backpropagation algorithm, and training datasets are essential for improving performance and generalization capabilities.
Absolutely. One important aspect of training BNNs is the role of learning rate and momentum. The learning rate determines how quickly the weights of the network are adjusted during training. A high learning rate can lead to overshooting and instability, while a low learning rate may result in slow convergence. So finding the right balance is crucial for effective training.
That's right. And momentum is another technique used to prevent oscillation or getting stuck in local minima during training. It introduces an element of persistence to the weight updates, allowing the network to continue in the same direction during consecutive iterations. This acceleration of convergence can help the network bypass poor local optima and improve overall performance.
Exactly. So adjusting the learning rate and momentum appropriately is essential in training BNNs effectively. It's all about finding the right balance between fast convergence and stability.
Moving on, let's talk about regularization techniques for preventing overfitting in Bayesian neural networks, BNNs. Overfitting occurs when the network performs well on the training data, but fails to generalize accurately on unseen data. One commonly used technique is L1 regularization, which adds a penalty term to the loss function and promotes sparsity by shrinking parameter values towards zero.
Another regularization technique is L2 regularization, which adds a penalty term that encourages smaller parameter values. This helps prevent overfitting by reducing the sensitivity of the network to input variations. Cross-validation can also be utilized to determine the optimal regularization parameters, further improving the network's generalization capabilities.
Absolutely. By implementing these regularization techniques, BNNs can effectively prevent overfitting and improve their ability to accurately predict unseen data.
Now let's discuss evaluating the performance of BNNs during training. One commonly used metric is the loss function, which measures the discrepancy between the network's predicted outputs and the actual outputs. Monitoring the loss function allows us to observe how effectively the network is fitting the training data.
That's right. Another crucial metric is accuracy, which quantifies the network's ability to correctly classify or predict outcomes. By monitoring accuracy throughout the training process, we can gauge the model's progress and identify potential issues such as overfitting.
In addition to metrics, visualizations such as learning curves can provide valuable insights into the network's convergence behavior. This allows us to fine-tune hyperparameters and optimize the training process for better performance.
Absolutely. Careful evaluation of performance metrics ensures the effectiveness and reliability of BNNs during their training phase.
Moving on, let's talk about parameter initialization as a way to improve the efficiency of training deep neural networks. It has been observed that initializing the network's parameters with small random values can lead to better convergence of the algorithm.
That's correct. Small random values ensure that the gradients computed during backpropagation do not vanish or explode, which can hinder the learning process. One popular initialization method is the savior initialization, which initializes the weights of each layer by drawing from a Gaussian distribution with zero mean and a variance that depends on the number of input and output units.
The savior initialization has been widely used in various deep learning architectures and has shown to improve their overall performance.
Now, let's discuss the advantages and limitations of BNNs. One significant advantage is their ability to learn and generalize from large amounts of data. BNNs have found extensive applications in various domains, such as image and speech recognition, due to their ability to handle complex patterns.
Absolutely. Another advantage is their scalability, allowing them to process large datasets efficiently. Moreover, BNNs can handle noisy or incomplete data, making them robust for real-world applications.
However, BNNs also have limitations. The training process can be computationally intensive and time-consuming. Additionally, they require significant amounts of labeled training data to achieve satisfactory performance, which may be costly and time-consuming to acquire.
And let's not forget about the overfitting problem. BNNs can become too specialized to the training data, resulting in poor generalization to unseen data.
So, while BNNs offer remarkable advantages, their limitations should be taken into consideration when applying them in practice.
Absolutely. One of the major challenges with BNNs is the computational expense and time-consuming training process, especially for large-scale datasets. This is because BNNs require multiple forward and backward propagation iterations on the entire dataset.
That's right. And another challenge is the choice of hyperparameters, such as learning rate and number of hidden layers. These hyperparameters significantly affect the performance of BNNs, and finding the optimal set often involves a trial and error process.
However, there are ways to overcome these limitations and improve the performance of BNNs. One approach is to utilize a larger dataset for training the network. This helps prevent overfitting and improves generalization.
Increasing the number of hidden layers and nodes in the network can also contribute to its improvement. This allows for a more complex representation of the data, enabling the network to learn and extract more relevant features.
Regularization techniques such as weight decay and dropout can also be used to prevent overfitting. These techniques help reduce the complexity of the model and improve its generalization ability.
Additionally, optimization algorithms like stochastic gradient descent with momentum or adaptive learning rate methods like ADAM can be employed to enhance the network's convergence rate and accuracy.
And let's not forget about exploring novel activation functions and network architectures specific to the problem domain. This can help overcome limitations and enhance the performance of BNNs.
Absolutely. By continuously improving and experimenting with these approaches, we can overcome the limitations of BNNs and further enhance their performance in real-world applications.
That's right. BNNs have proven to be highly effective in various fields, such as healthcare and finance.
In healthcare, BNNs can be training on large datasets of patient information to accurately predict the likelihood of certain diseases. This helps healthcare professionals make informed decisions and provide timely interventions.
And in finance, BNNs have shown promising results in predicting market trends and making investment recommendations. Their ability to process and analyze vast amounts of financial data allows for improved decision-making and potentially higher returns on investments.
The application of BNNs in real-world scenarios has the potential to revolutionize various industries and create significant impacts on society.
Absolutely. The advancements in BNNs continue to improve their performance and applicability in solving real-world problems.
One area where BNNs have had a significant impact is in image recognition and computer vision. These technologies involve the identification and categorization of objects, patterns, and features within digital images and videos.
And with the development of deep learning algorithms and convolutional neural networks, CNNs, BNNs have shown remarkable ability in recognizing complex patterns, detecting objects, and performing tasks like facial recognition and object tracking.
That's right. And these advancements in image recognition and computer vision have great potential in various sectors, such as healthcare, security, autonomous vehicles, and robotics.
Moving on to another area, BNNs have also played a crucial role in natural language processing, NLP, and speech recognition. NLP refers to the ability of a computer system to understand, interpret, and generate human language.
In speech recognition focuses on converting spoken language into written text. By incorporating speech recognition into BNNs, researchers aim to build speech-to-text translation models that can automate tasks like transcription and voice assistance.
These advancements open up new avenues for the application and improvement of BNNs in various domains. They allow for more intuitive and user-friendly interactions with the network, enabling us to communicate with computers more naturally.
Financial forecasting and stock market prediction are other areas where BNNs have gained significance. By analyzing complex financial data, BNNs can predict future market trends and help investors make informed decisions.
BNNs are able to capture and understand the intricate relationships between various financial indicators and stock market behavior. This can be incredibly valuable in minimizing financial risks and maximizing returns.
Additionally, BNNs have become a widely used technique in the field of artificial intelligence due to their ability to effectively model complex relationships between input and output variables.
That's right. BNNs are trained using the backpropagation algorithm, which allows the network to adjust its parameters by iteratively computing the gradient of the error function. This enables BNNs to accurately classify input data and make predictions.
However, BNNs do face challenges such as the need for large amounts of labeled data for training and potential for overfitting. But ongoing research and advancements in BNNs continue to improve their performance and applicability in various domains.
Looking towards the future, we can expect to see more efficient algorithms for training neural networks, allowing for faster convergence and more accurate predictions.
Absolutely. The integration of BNNs with other emerging technologies, such as deep learning and big data analytics, is also expected to enhance their overall performance.
And we can't forget about the utilization of BNNs in complex tasks like natural language processing and image recognition. As researchers continue to push the boundaries of AI, we can expect BNNs to play an even larger role in these areas.
Current advancements and ongoing research in BNNs have already contributed significantly to the field of AI. Deep learning techniques, weight initialization techniques, and overcoming the limitations of gradient descent are just a few examples of the progress being made.
And let's not forget about the integration of BNNs with other technologies like edge computing and quantum computing. This shows promising potential for further advancement and application in various industries.
The continuous advancements and research in BNNs are truly opening new doors for enhancing the capabilities and potential of artificial intelligence systems.
Absolutely, Samantha. One potential area of advancement mentioned in the article is the development of more efficient and effective training algorithms for BNNs. Researchers are exploring alternative optimization techniques such as genetic algorithms or swarm intelligence to improve convergence speed and overall performance.
That's right, Avery. By finding new ways to train BNNs, we can enhance their accuracy and efficiency in various applications. Another avenue for improvement is the integration of BNNs with other emerging technologies like deep learning or reinforcement learning. Combining the strengths of different algorithms can further enhance the capabilities of BNNs.
Exactly, Samantha. By leveraging the strengths of different algorithms, we can achieve even higher levels of accuracy and efficiency in tasks like image and speech recognition, natural language processing, and data classification. This has the potential to revolutionize the field and unlock new possibilities for the application of BNNs.
Additionally, the advancement of hardware technology, specifically the development of specialized hardware for BNNs, could lead to significant improvements in computational efficiency and real-time processing capabilities. This means that BNNs can process data faster and more efficiently, making them even more powerful in solving complex problems.
That's a great point, Samantha. The combination of improved training algorithms, integration with other technologies, and advancements in hardware technology truly shows the promising future of BNNs. These developments have the potential to revolutionize various industries and domains from finance to healthcare to engineering.
While the future looks promising for BNNs, it's important to consider the ethical implications and impact on society. One primary concern is privacy, as BNNs often require large amounts of data to train effectively. There is a risk of individuals' personal information being exploited or misused.
Absolutely, Samantha. The transparency and accountability of BNNs are also crucial. By understanding how these networks work and ensuring transparency in their decision-making processes, we can address potential biases and discrimination in the data used to train them.